Okay, so we have seen the signal circuits, and also we have gone into the details of the integration of microsystem and microelectronics. Now, we take up some special cases like the pressure sensor, its design concepts, processing and packaging. So, in this presentation we discuss concepts and types of pressure sensors, definitions and design criteria, single crystal piezoresistive pressure sensor, then pressure sensor packaging, a glimpse of that I will give you also. So, the pressure sensor involves or it requires a membrane, thickness decided by your pressure requirements, and membrane is anchored all round in these portions to a thick frame, so that it is free to move up and down when it experiences a pressure, fluid pressure, and that membrane is usually in micro machine devices, it is silicon, and you have a sensor element. We will discuss what are these two. So, the membrane, or you can call it as a spring also if you like, is usually or invariably made of single crystal silicon material. That is because the silicon is a very good material, mechanical material. It has high Young's modulus, high yield strength, all those advantages are there, even comparable to or better than steel, excellent mechanical material. The added advantage is, unlike some of the metals, metallic membranes, silicon is free of creep, fatigue, hysteresis, virtually free. The creep meaning, what is the implication of creep? If you heat most of the materials like metals, you heat it to almost slightly above half that melting point, there is a chance of this being, there will be warpage of that membrane. Whereas, silicon melting point is 1410 degrees centigrade, you can go right up to 1200 degrees centigrade, it does not, there is no practically no warpage. So, that is what is meant by there is no creep. That is what it has made it possible to make integrated circuits by processing at very high temperatures with using silicon. Then you can keep on, if you are using it as a membrane, you can keep up and down large number of times, you can operate it a million times, there is no fatigue and there is no hysteresis. In the sense, if you apply pressure and if you release the pressure, it will quickly come back to its original position. In metal membranes, it takes a while to come back to its original position. So, during that time, you will have some signal coming out of the pressure sensor. These are some of the main advantages of using silicon as a membrane, and it can be processed very easily using the conventional integrated circuit technology. Now, the sensing element that you put on the membrane, okay, they can be of different types. The most popular ones are piezoelectric, capacitive and piezoresistive. I will just go through what they are quickly. The piezoelectric sensing. Here, a piezoelectric crystal like quartz or PZT. PZT is lead zirconate titanate. So, these are very good piezoelectric materials. These crystals give electrical output when subjected to stress. So, you can mount them on the membrane. Okay. So, when this membrane is subjected to pressure, let us say from the bottom end, then the membrane will deflect up. This is anchored here. The membrane will deflect up and there will be strain in the membrane. The strain will be transferred on to this, strain and stress will be subjected transferred on to the PZT or piezoelectric crystal, and then a voltage will develop across the two terminals of that PZT or piezoelectric crystal, top metal and bottom metal, you will have the output voltage. Okay. You can see that you are not using any power supply for this, straight away you get the output. When you subject it to pressure, the device is subjected to pressure, you will get the output straight away, excellent for usage remote places. Okay. But the problem is, this PZT has to be glued, it is externally glued onto the membrane. Okay. The pellet opposite is glued onto this, and this is not part of the conventional integrated circuit technology. So, that is not disadvantage, but still you may say I can deposit some PZT polycrystalline materials and use it, but then the sensitivity will go down if you use such materials. Now, but more serious disadvantage is it is not suitable for static pressure, because if you have static pressure, the membrane deflection is constantly there and the strain is constantly there, and constantly the charge developed across this piezoelectric crystal will be leaking. It is like a capacitor being charged, the capacitor charge will leak. So, for static pressure measurements you cannot use it, but for dynamic measurements you can use it. If the pressure is continuously varying, then this is a very good method. It is like varying the voltage across a capacitor, then you can see the capacitance changes. So, this is the main drawback of that. Now, let us take a look at the capacitive pressure sensor. The capacitive pressure sensor, you can see the membrane is here, and you put another top wafer, bond it onto this wafer with a gap. So that when this membrane experiences pressure from the bottom, okay, that will deflect up, then the gap between the top wafer and this membrane is reduced, the capacitance will go up. Okay. So, this is operating on the principle of changing the capacitance due to change in the distance between the two electrodes. So, how much distance changes depends upon the pressure. So, it is very good for its sensitivity in this type of sensors, capacitive sensors, pressure sensors is excellent, and also this capacitance change is practically independent of temperature. So, temperature coefficient of sensitivity is absent. This on the disadvantage side, the main thing is the capacitance voltage characteristic is not linear. So, the capacitance change will not linearly vary with the displacement. So, it is not a linear function of the pressure. So, you may have to do linearizing circuits to accommodate large range of pressures, and you definitely need electronics in this system, because you have to convert capacitance to voltage. So, these are the added requirements for capacitive sensing, otherwise it is very highly sensitive and it is temperature insensitive. That is the biggest merit. So, you can see the third one, piezoresistive sensors. A piezoresistive sensor, here what you do is, I have shown here a 3-dimensional picture where a membrane is present, which is anchored here onto a glass substrate. So, this portion, center portion of the membrane is free to move up or down when it experiences a pressure. So, that membrane will experience a stress and will undergo stress, suffer stress, and the stress will be transferred onto the resistors, 1, 2, 3, 4 resistors, which are located like this on the membrane. If this is the membrane top view, you have these 4 resistors which are located there. We have discussed little bit about that in the previous lecture. Okay. So, these resistors experience a change in resistance when it is subjected to stress. For example, as I mentioned already in the previous lecture, the resistance R, which is mounted perpendicular to this edge, will experience a longitudinal tensile stress, and its value will go up if it is a p type resistor. These are semiconductor resistors. Then if it is mounted parallel to this edge, it will experience transverse stress, that is perpendicular to its length. Then if it is a p type resistor, the resistance value will go down. Okay. So, you mount these resistors whose values go up, you mount on opposite arms of the bridge. The ones which go down, you mount on the other two opposite arms of the bridge. So, that when there is unbalance, this bridge will give an output voltage. The unbalance comes because of this delta R, delta R, delta R present here. You will get an output voltage which is equal to, if all the delta R are same, it will be delta R divided by R into input voltage. So, you can see the sensitivity of this sensor would depend upon how much is the delta R by R, and how much is the delta R by R would depend upon the strain experienced by the resistor due to the strain on the membrane. Now, on the merit side, before we go to that, this change in the resistance takes place because of two things. One, due to the dimensional changes which happens in the conventional strain gauges, plus secondly, in the semiconductor piezo resistors, the resistance change takes place also due to the change in the resistivity. So, that change is dominant, change in the resistivity. Okay. So, that is a, we are not getting down into physics of that, it is due to change in the mobility of the carriers when it is subjected to stress. The merits, simple to fabricate, all that you need to fabricate a membrane, on that realize these resistors. How to do that we will see as we go on. No need of electronics. For example, if delta R by R is just 0.1%, input voltage is 1 volt, you will get 1 millivolt. If it is 10 volts input, you will get 10 millivolts, which can be easily measured. But you may need electronics for further processing, that will be a different issue. Linear characteristics, okay, the output voltage will be linearly related to the change in the resistance, which linearly related to the strain, which again is linearly related to the stress or the pressure. So, that is the main advantage of this piezoresistive sensors. On the, you do not get everything free, what you have to pay for this is the, what will on the disadvantage side is the temperature coefficient of resistivity and temperature coefficient of sensitivity is finite in this type of sensors. Okay. So, with seeing these things, we will go into some of the details of this piezoresistive sensors. So, I have shown that the isometric view of the silicon micro machined pressure sensor. The membrane is realized by micro machining technique. You can see that angle between the bottom surface, which is 100 wafer, and this 111 plane, which you have discussed in your technology lectures. So, you have the membrane. Thickness can be precisely controlled based on your design. Then these red colored ones are the resistors R1, R2, R3, R4, R1, R2, R3, R4 are put like that. Now, in this case, the this is different location that I have shown here. R2 and R4 are arranged perpendicular to this dotted line, which is nothing but the location of the membrane. So, those two resistors experience longitudinal tensile stress and the values will go up, R2 and R4. Okay. R2 and R4, the values will go up, okay, and the R1 and R3 will go down in this particular case. So, these at the edges here will go up, these at the center of the membrane will go down, resistance, okay, because of the at the center you will see that the, if you plot the stress along this line, if you plot the stress along this line, center line of the membrane, it will be tensile at the edge, is positive meaning tensile. As you move from left to right along the center dot, what happens is the stress is tensile here along that direction. It keeps, you can see the square type of membrane, W is 500 micron, length is 500 micron. This is the lateral dimension of the membrane. So, at the edge minus 250, the width is 500 microns, I take the center at 0. So, minus 250, 0 is here, minus 250, the stress is 200 newtons per millimeter square, which is actually 1 Newton per millimeter square is 10 bar, 10 atmospheres. This is 2000 atmospheres. When the membrane is subjected to a stress perpendicular to the plane, is subject to a stress of 3 atmospheres, 3 bar. 1 bar is 3 bar, 1 atmosphere is 1 bar, 3 bar is 3 atmospheres. So, in fact, if you are familiar about other dimensions for the pressure, 1 bar is 760 torr, which is 760 millimeter of mercury, or 1 Newton per millimeter square is 1 Pascal. So, 1 megapascal is 10 bar. So, if you have 3 bars of pressure on the membrane, all over the membrane, okay, you subject it uniformly all through the membrane like that, perpendicular, then the stress will vary from the edge to the center and to the edge. At the edges, on the both edges, minus 250 and plus 250, the stress is maximum, and what we are talking of is the stress in that direction. If you put a resistor there, you can call it longitudinal stress along this direction. So, that stress for a 3 bar pressure is 2000 bar. You can see that the applied pressure of 3 bar is amplified in terms of stress at the edges. So, the membrane virtually acts as a pressure or stress amplifier. So, that if you put a resistor at these edges, you see the amplified stress. So, for a small pressure, there is large amount of stress experienced by these resistors, which actually is transferred from the stress on the membrane. So, as you go from the left hand side to the right hand side here, it varies from 2000 bar, somewhere here, somewhere about middle of between the center and the edge, the stress is 0 on the top surface of the membrane. As you go down further to the center, the stress is negative, meaning it is compressive. So, go to the right, it becomes less compressive, 0, then tensile. So, you have got the stress variation, tensile, less tensile, compressive, less compressive, tensile, and maximum at the edge. So, you can place the resistors at the edges here, they will experience tensile stress. The resistors at the center, because that is compressive, they will experience compressive stress. Those values will go down. Okay. Now, you can just go further. I just have to point out here this R1 and R2, they actually go up, and R1 and R3 go down. So, that if these two go up, the polarity will, okay. If this go down and this goes up, R3 goes up, the voltage will be positive here, and if R1 goes up, the polarity R4 goes down, the polarity will be negative here. Okay. One more thing that I want to point out here to you is that if you keep the width constant and if I keep on varying the length of the membrane, the stress concentrations all through will increase. For example, if I make it double, width 500 micron, length 1000 microns, the stress will actually become much larger than that. You can see it goes up from 200 newtons per millimeter square to about 350. Same way here, the compressive stress also goes from 100 to about 200. Okay. Now, the definitions. The strain in the crystal structure deforms the energy bands, and that is why the resistivity changes. That is the physics of that. The gauge factor, you have certain parameters which you have to define, that is the gauge factor. Gauge factor is delta R by R, change in resistance divided by original resistance divided by strain, and strain is delta L by L. So, the resistance rho, resistance R is actually rho L by A. Okay. So, delta R takes place due to change in rho L and A. Okay. So, delta R can be written in terms of all these changes as rho by A into delta L, L by A into delta rho, and rho into L into differential of A 1 by A, that is delta A by A squared minus. Now, there is one term one has to remember, delta L by L is actually the strain epsilon. Delta A by A is the change in the transverse direction, and that you can put in terms of the diameter as twice delta d by d. So, you will rewrite this whole thing as delta r by r divided by r. When you divide it by r, what you will get will be delta rho by rho delta L by L minus twice delta d by d. Now, in mechanics, you have got another parameter to remember, that is the Poisson's ratio nu. When you subject a device to a stress in the longitudinal direction and you pull it, there will be a change in the lateral dimensions. That change in lateral dimension is defined as the nu. So, the ratio of this change in the lateral dimension to the change in the dimension in the linear direction is defined as nu. So, if that goes up, the lateral it goes down. So, that is the negative sign that is put. So, what you do is substitute for delta d by d as minus delta L by L, that is minus nu into epsilon. So, put them all together, you get G is equal to delta r by r divided by epsilon, which is equal to delta times rho by delta rho by rho plus this is nothing but delta L by L is nothing but epsilon, minus minus cancelled and plus twice nu. Okay, since you are dividing by epsilon, that goes off. So, here nu is actually due to the change in the dimensions, delta L by L. Okay. Now, due to the physical dimensions changes, but the first term is due to the change in the rho. In metallic piezoresistors, main change in resistance delta r by r takes place due to change in this physical dimensions, okay, and delta rho by rho in metals is negligible. So, in those metallic strain gauges, the gauge factor, which is actually first term is negligible, you get 1 plus 2 nu. If I take nu as 0.5, this will be 2, 1 plus 2 into half, that is 1 plus 1, that is 2. So, you will get a gauge factor anywhere 2 to 5 or so for metals. Whereas, in semiconductors, this term, which is due to physical change, is almost similar to the metal, small 2 or 3 due to that the gauge factor, but delta by rho by epsilon is large quantity, that will be the total number will be close to 100. So, the benefit of using semiconductor resistors is that the gauge factor, that is change in resistance due to the change in strain, will be extremely large compared to metal strain gauges. Okay. So, to take a look at some numbers, metal foil will have gauge factor of 1 to 5. So, this gives you an idea how much delta r by r for a given strain. So, if you can measure delta r by r, you can get information on strain, and if you obtain the information on strain, you can obtain the information on stress, which can be correlated to the pressure. Thin film metals 2 is the gauge factor. Diffused semiconductors, that is single crystal, it is 80 to 200, very large. Polycrystalline, that is not single crystal, made up of number of single crystal structures, that is about 30, that is the gauge factor. Okay. Now, we take a look at further on the piezoresistive. See, this term that I have introduced to you here is the gauge factor, which tells you delta r by r related to strain. Delta r by r by strain is the gauge factor. Now, there is one more term similar to the gauge factor, which is related to, which relates the change in the resistance delta r by r to the stress, that is the piezoresistive coefficient. Okay. So, delta r by r is related to stress sigma through this proportionality constant coefficient pi. Pi is the piezoresistive coefficient. Okay. Now, you recall we defined delta R by R as gauge factor G into strain, and in this we define delta R by R as piezoresistive coefficient into stress. Okay. So, you can define it delta R by R with respect to stress through piezoresistive coefficient, or delta R by R related to strain through the gauge factor. Both are allowed. Okay. You can remember one of them, you can correlate, because sigma divided by strain, stress divided by strain is called Young's modulus. In applied mechanics, all of us know that this is Young's modulus. So, gauge factor is related to the piezoresistive coefficient pi through the Young's modulus sigma by epsilon, and that is Young's modulus usually defined by a symbol E. Do not confuse with the electric field, but this is a general symbol that is used, E. So, the gauge factor is related to the piezoresistive coefficient through the Young's modulus. Okay. But without confusion, delta R by R is piezoresistive coefficient into stress, or delta R by R is gauge factor into strain. The Young's modulus is about 190 gigapascal for silicon. Gigapascal is 10 to the power of 9 pascals. 1 pascal is 1 Newton per meter square. Okay. Now, let us take a look at further the effect of longitudinal stress sigma L and sigma T on R. See, we have shown, we will see where these stresses should be located to further. Supposing this membrane shown by color is subjected to stress perpendicular to that from the top with a pressure P, whatever you need to say, if you say in pascals, if you subject it to the stress, and from the analysis, analytical number, you can see a formula is available for you to correlate this applied pressure to the stress at this edge of this membrane in that direction, x direction. Okay. If I put a resistor there in that direction perpendicular to this edge of the membrane, perpendicular to the edge of the membrane, that will be longitudinal stress that we are talking about. Stress in x direction is along the direction of the membrane, I am sorry, along the direction of the resistor where the current flows, that is longitudinal. So, sigma x for a pressure P will depend upon the ratio of the membrane dimension. For example, if I take a square membrane of side 2A, if I take 0 at the center of the membrane, this is plus A and the other edge is minus A. So, if 0 is at the center, the stress at the edge here, at the near this edge of the membrane is applied pressure multiplied by A divided by thickness H whole square. H is the thickness of the membrane. Okay. So, you can see if the pressure is 1 bar, 1 atmosphere applied onto this perpendicular, the stress at the edge of this membrane is 1 bar into A by H whole squared. If 2A is 500 microns, that is the width, or the length of this side length of the membrane is 2A equal to 500 micron, and if H thickness is 10 microns, 1 micron is 10 to the power of minus 4 centimeters. So, if thickness is 10 microns, this is 250 divided by 10 whole square, I am sorry, 250 divided by 10 is 25, 25 whole square is 625. So, if I apply 1 bar pressure to this membrane perpendicular, the stress at the edge will be 625 atmospheres, 625 bar. And in a y direction, whatever stress is experienced there, x direction multiplied by the Poisson's ratio, that is 0.3 times that. Okay. For silicon it is about 0.3. It will depend upon the material, it will be of that order. So, on the resistance R which is mounted like this, sigma L is P into A by H whole squared, sigma transverse perpendicular to this direction along the length of the longitudinal is, if I have the resistor like this located, that current will flow in that direction, you call that direction as longitudinal, and perpendicular to that, that is the width of the resistor. So, that is called transverse. So, if I have a resistor located like this, longitudinal is P into A by H whole square, transverse is nu times that. Okay. Now, let us put this in terms of the piezoresistive coefficient, okay. Because for the material you will know how much is the piezoresistive coefficient or how much is the gauge factor you will know. So, therefore, we will see sigma L is P into A by H whole square, therefore, and sigma T is nu times P into A by H whole square. So, the total change in the resistance is due to the combined effect of these two, which is longitudinal piezoresistive coefficient into the stress. Notice delta R by R is sum of the effects of longitudinal stress and transverse stress. Pi L into sigma L, longitudinal resistive coefficient multiplied by longitudinal stress plus the transverse value. Now, delta R by R you can put it as now pi L into sigma L is P into A by H whole squared plus transverse stress into nu into P into A by H whole squared. Okay. Now, this pi L and pi T are opposite. For single crystal membrane, the pi transverse is negative of pi longitudinal, because of simple fact that the longitudinal stress will increase the resistance for p type, transverse stress will decrease that. So, that is why this negative sign takes care of that. Substituting that, you will get delta R by R is pi L into P into A by H whole squared, which is common, and pi L plus pi T, which is pi L into 1 minus nu. So, you can see the whole thing is pi L into P into A by H whole squared is 1 minus nu, delta R by R. So, you can now tell very comfortably that if you know the delta R by R, pi L would be, you will know other dimensions are known, you can tell what the pressure is. That is how the pressure sensor works. So, delta R by now from here is pi L into pressure into A by H whole squared. A is half of the width of the membrane size by H whole squared into 1 minus nu. Nu is Poisson's ratio about 0.3. So, you can express this is in terms of the piezoresistive coefficient. You can express it in terms of the gauge factor also, because you know that the pi L and G L are related through the Young's modulus. So, I just divide this by this entire thing. This is the stress divided by Young's modulus gives me strain. So, G L into strain gives me delta R by R. Either way, this way or that way, you can express it. The key thing is you must know the stress or the strain. Stress divided by the Young's modulus is strain. Then you multiply it by G L or pi L, gauge factor or the piezoresistive coefficient. With that, we have discussed the definitions. Now, let us get back to the single crystal piezoresistive pressure sensor, how it works. So, we have already seen this. This is the membrane which is created with the cross section of the membrane, which is prepared by etching silicon from these portions by the anisotropic etching, which is already well known to you. And on this membrane, I have shown two here, because if you see the top view, the membrane will be here, and if I take the cross section here, I can see only these two resistors. So, the four resistors are located like this R 1, R 2, R 3, R 4, because at the edges, in the middle at the edges, the stress is maximum. longitudinal here, longitudinal here, transverse here, transverse here. That is the key thing. Two of them should increase, other two should decrease. That is why you chosen the locations. So, in this case, if all the r values are same, then you can put V naught is equal to delta r by r into V in. We have said this number of times, and delta r by r, you can see here, you can measure V naught in terms of V in. Both V naught and V in will be known, delta r by r is known. From delta r by r, you can determine what is this quantity is. Okay, you can calibrate it actually. You will see, you can, for a given sensor, you find out what is V naught by V in, and you do not start computing delta r by r. You plot V naught versus pressure, then you will see. We will go on seeing to that. So, delta r by r is a measure of this entire quantity. Okay. So, here this entire thing is the stress into the piezoelastic coefficient. Let us take a look at the sensitivity and the burst pressure. What is sensitivity? Sensitivity is V naught divided by the pressure. Okay. V naught is delta r by r into V in, which is P into stress, this is this quantity, into input. Now, in this term you see the pressure P. So, sensitivity is delta V naught divided by delta P. Delta V naught depends upon delta P, and of course, for a given voltage you divide by that. So, this is the quantity, that is pi L into A square by square into 1 minus nu, straight away that will give you. So, to tell you in other terms, sensitivity will depend upon the material that you have chosen, longitudinal piezoelastic coefficient, and A by H ratio. A is the half of this side, H is the thickness. If you want to increase the sensitivity, choose for a given dimension, go on making the thickness less and less, which will become more and more sensitive. More output will be there for a given input voltage, for a given change in pressure. But there is upper limit on this sensitivity, that comes up from the burst pressure. See, for example, if I keep on increasing the pressure on this membrane, the maximum stress is experienced at the edge, which is applied pressure into A by H whole squared. So, if I can go to a maximum pressure. At a particular maximum pressure, the stress at the edge will reach a maximum value, which will be the critical pressure. That is the point at which the membrane will yield, it will burst. Okay. So, that critical pressure is 7 gigapascal for silicon, that is 70,000 atmospheres. So, okay. So, the maximum pressure that you can apply will be decided by when is the critical pressure is reached. So, if H is smaller, this factor will become larger and larger, and for the given pressure, the sigma maximum will be reached at a lower pressure. So, the maximum pressure that you can use will be less if the sensitivity is more. So, the guideline is thinner the membrane, your sensitivity will be better, but the maximum pressure that you can use will be lower, because it will burst at a lower pressure. Okay. But can you go right up to that maximum stress? That is decided by what is the upper limit, other upper limit. See, there is a relationship based on the theory of plates. The pressure is related to the deflection W naught divided by H by this relationship. A by H is the membrane dimension. Okay. So, if I keep A constant, if I keep on reducing H, this equation tell you that first term is linear, W naught by H is linear. If second term is negligible, the pressure and deflection are linearly related. So, your delta R by R or the sensitivity will be linear function of pressure. Okay. If you increase the pressure, the output voltage will increase linearly. Now, if I keep on increasing the pressure, the deflection will become more and more. At a certain point, the deflection will become comparable to the thickness. For example, if the deflection is if deflection is 0.1 times the thickness, that is, if h is 10 microns, if the deflection is 1 micron, you can see this second term will become will some factor, it will become comparable to this first term, about 10% of that, that is at the pressure of 2.2 bar. In other words, you must stop using the sensor when the deflection becomes W naught becomes comparable to the thickness. So, for this example where A by H ratio is 25, then at a pressure of about 2 bar, it becomes, the second term becomes comparable to the first term. So, that means you cannot use it beyond 2 bar, though your burst pressure will be much higher than that, you do not go on using till burst pressure. So, the ultimate limitation comes up from these linearity considerations. Okay. Now, there are different types of pressure sensors. So, once you understand this concept, we will take a look at the different types of pressure sensors. Absolute pressure sensor, you measure the pressure relative to vacuum. That means, you have a cavity which is completely sealed and there is vacuum inside the cavity, and the membrane, it gets deflected due to the external pressure, that is absolute. You are measuring the pressure with respect to vacuum. The second type of pressure sensor is the gauge pressure. You see, in the gas cylinders you put a gauge. That gauge is measuring the pressure with respect to atmospheric pressure. So, for example, if the cavity is filled with 1 atmosphere pressure air, then whatever you see outside is over and above that pressure, how much is the pressure? That is the gauge pressure. So, it is called gauge pressure sensor. If you are measuring, for example, blood pressure, they measure the blood pressure relative to atmospheric pressure. So, when you say blood pressure is 80 by 120 during systolic and diastolic, that means it is 80 millimeter of mercury and 120 millimeter of mercury with respect to the atmospheric pressure. Okay. So, vacuum gauge, you measure vacuum, that is also a gauge pressure with respect to atmospheric pressure, how much it is. So, you call it as minus 10 to the power of minus 1 minus 2, you say that is the fraction of the atmospheric pressure. Then you have got differential pressure sensors, which measures actually the pressure on top and bottom on both sides of the membrane. These are used when you want to monitor the pressure from both sides and you want to keep a pressure constant across a membrane, and if you want to vary the two pressures, inside pressure 1 bar, outside pressure 1.5 bar, and inside pressure becomes 1.5 bar, outside pressure also you keep increase it by 0.5 bar. So, difference is maintained 1.5, that is the differential pressure. Now, this is the pressure sensor, which is a 3-dimensional picture. You put these 1, 2, 3, 4 resistors, cross section are shown here. This is anchored in these portions. This silicon membrane is stuck to this glass in these edges, so that this is rigid and this can only move. The way you make that is, make a membrane, realize these resistors, first anisotropic etching of the silicon wafer to realize the thin membrane, implant or diffuse boron into these regions to realize the resistor. Then interconnect the 4 resistors to form the Wheatstone bridge, then bond this glass onto this. Now, to go through quickly, I do not have to do this very in detail for you, because because you have done the lithography. So, I have shown the cross section. Take 100 silicon, let us say 230 micron thickness, grow oxide, spin photoresist, expose that photoresist through this is a mask, photo mask, there is a pattern here. So, light can go through this pattern, it will get exposed here, positive photoresist, you can develop it, the photoresist is removed from here. So, you got the photoresist here, I show it once again here. I am quickly going through this lithography step because you already know. So, you have the photoresist here, remove the photoresist from here, post baking etcetera you do at 120 to harden the photoresist. Then using the photoresist as the mask, these are cross sections, etch the silicon dioxide using hydrofluoric, dilute hydrofluoric acid. So, you got the photoresist, below that oxide, this oxide is removed. You protect the backside oxide because do not remove the photoresist. Then after this, once you etch this oxide, strip off the photoresist from both sides. So, from starting from the oxide all over, you have ended up the oxide removed from here. Now, this one you put it in the potassium hydroxide etchant. So, in this portion you can etch silicon, and from your knowledge of this KOH etching you will see that it will go in this direction controlled by the 111 plane. If you etch up to 220 microns, the dimension is if the size left out here is 500 microns, by when you etch 220 microns, you can calculate that the size of this opening here is 500 plus 220 divided by 0.7, that is 810 microns. So, what you have to in the design, what you have to do is, in the pattern you must design 810 microns pattern size. When you have that pattern opened, when you etch it to a depth of 220 microns, you will end up with a membrane of thickness, if this is a 230, 10 micron thickness and 500 micron dimensions. I strip off this oxide, you get this, okay, and I flip it upside down, you get the membrane. This is the cross section. Looking at the top of this, if you look at that, I am showing one device, number of devices will be there on the wafer, I am showing one part of the wafer, that will look like this, nothing will be seen, the cross section is like that. See, you want to put the resistors on the top of this membrane, for that you will do lithography, you must see it from the top. When you see, you must see where the membrane location is. One way of doing that is shine infrared light, IR light from the back side of the wafer, then you can see this particular thing transparent like that, because IR can go through from bottom, and if you put a video camera on the top, you can see this membrane. Okay, I have shown this, and then by lithography technique from the top, you can realize you can grow oxide, open window in the oxide in these portions and diffuse resistors here. That is the technology part of it. Okay, you can put the resistor in these portions, and then you can make connections between the two. So, this is IR lithography, or you can have a machine where you can have facility for backside aligning, using storing the pattern on the backside and ability to see it on the top. So, you can put the resistor like this or like this, either way. Here this will experience longitudinal stress, tensile stress, these two transfers. Here these two will experience longitudinal tensile stress, these two will experience longitudinal compressive stress. These two will go up, these two will go down. Here these two will go up, these two will go down in value. Okay. Now, when you see from the IR aligner, this is what you will see, this is the membrane is, these are the resistors which you can see. So, you can precisely see where to locate these resistors. This just I have taken the photograph from the video camera. And if you look at the back side of this membrane, if you look from that side, not IR, through microscope you see, that is how it will look. This is the edge where we etched, this is the sloping side, and because it is sloping, when you see at a microscope, this portion looks dark because light will not be reflected there. So, when the light is not reflected, it will look dark. So, you see this is the bottom of the etched portion, that is the membranes looking from the back side, this is the top of the wafer on the back side. Okay. So, the couple of things I want to point out here. The this particular thing I just skipped that. See, you can actually either do IR exposure or store this pattern focusing from back side, store it on the video camera, then look from the top, have a pattern on this side, align them together, then you can bring this resistor in that side. That is another way of doing that. Anyway, what I am trying to point out is the resistors should be, if you do not have the ability to align these resistors with respect to this portion, that will move away from this membrane and that will not experience the stress. Okay. Now, part of this thing is the how to package this. I have come almost to the end of my discussion today, because the more details about these we will discuss in the next session, including the packaging. See, what I have shown here is the cross section of the one device, okay, and I have not shown the resistor here. Resistor is kept on the top, somewhere here it is there, and the wires are there on the top that are not shown. So, what you do is you mount this die on a header. This is actually a thick metal plate which is gold plated. Onto that you can mount this either by a technique known as the eutectic bonding, that is just keep the silicon in contact with this gold plated plate and just heat the temperature to about 400 degrees centigrade. The silicon gets leached into this the gold gets leached into this silicon to form an alloy of gold and silicon. That alloy is a continuous transformation from silicon to this from gold to silicon, gold plated material to silicon. So, this pressure sensor die will be rigidly held to this header metal plate by this bonding, or you can solder it. There is an alternate way. So, once you mount it on that, see, this cap will not be there at that point. You will have this header, on that you have mounted this, then in the header itself there will be leads. In my next presentation, I will show those full details of those leads. You will have leads going through these holes through this header, and this is metal, this is metal. In between them there is some insulating material, so that there is no shorting between the header and this wire, this lead metal. This is thick metal. So, using a machine, there will be a pad on this region. Okay. You can bond wire onto this using a machine called the wire bonding machine. Take the other end of the wire, which is just about 25 microns, take it and bond onto this. You can do this by ultrasonic bonding. The ultrasonic bond is actually you have the wire bonded here, then taken to the other end here, and just you mount it on that point, and just mount it on that point, that will be vibrated like this. When you vibrate it, any little oxide that may be present on surface will be removed, and there will be these wires will be either aluminum or gold wire, okay. And this post will be actually be gold coated. So, when you just hold it onto that and vibrate it like that, local temperature will rise and there will be plastic flow, it will just bonded onto that. If you take two surfaces, just rub it like that, there will be the local temperature will rise and it will bond. That is the trick that is done here. There is no solder is being used. So, one end of the wire is bonded here, other end is taken and bonded onto the other end. So, with that you have mounted this die and all the wires you have connected to that 4 bond pads of this piezoresistor connected here. Then you have to close this, so that from the outside atmosphere with a cap, and this resistor, I am sorry, this is actually completely sealed. So, the pressure on the other side of the membrane is not changing. You can change the pressure by means of this opening here, you can apply pressure through this. So, the membrane can deflect on this side. Okay. This more of these details in my next presentation you can see. Okay. Now, other way is actually you can also use, instead of mounting it directly like this, first mount this on a glass plate, and the glass plate is attached onto the header through this. This is just a bit more sophisticated technique compared to this. Now, to see here more of this, I will just take you through some other region. The top of this particular, this is I am not showing the die here. You can see die is put on this. The die will look like this. For example, you will have a, see here, these are the bond pads. This is the resistor and the wire is connected on the top of the surface of this wafer itself. That is a pad onto which you will do the wire bonding. You will do the wire bonding onto that and take it out from there outside. Okay. You bond it onto that and take the wire out from there, bond onto the post on the header. So, this is what I mean by bonding pad. So, this is what is shown here. Bond pad is there, resistors are located on the membrane, from the bond you can connect to this one. So, with that I think I will close my discussion today. We will continue on this, on a particular case study of a pressure sensor with more details of this, making use of polysilicon piezoresistive pressure sensors. Thank you.